Hello, good morning everyone, or at least it's morning for me when I'm recording this. You could be watching this at 11 p.m. for all I know. What I want to do is just talk to you very briefly about where vectors meets the physics we've been talking about. So I want to just sketch out for you from like 10,000 feet up how you apply vectors to the kinematics equations that we already know and to Newton's second law, right? So we knew all along that those variables were represented by arrows, but now you know formally how to break them into components and reassemble them back into magnitude and direction. So let me just walk you through the equations the way they're meant to be. Okay, so let's start with kinematics. So you can do this with any of the kinematics formulas. I've got the workhorse here for the evolution of the velocity vector in time, right? The final velocity vector is equal to the initial velocity vector plus the acceleration vector times the amount of time that's gone by. So we're really actually never going to use the equation in its full vector form like this unless you just want to sketch out some tip-to-tail arrow additions to get like a conceptual idea of what's going on. But if you're actually doing numerical problem solving, you're going to break all these vectors down into their two components, right? And if you have a three-dimensional problem, you would have three sets of equations, right? If it's only one dimension, it's fine. You don't even really need the subscripts anymore, and you get right back to the original equation. But generally speaking, what you do is for every vector in the equation, they're all vectors except for time, you are going to pull out and write the equation over in terms of the components, right? So here is that equation rewritten in terms of the x components, right? So what this is saying in words is the final x component of velocity is equal to the initial x component of velocity plus the x component of acceleration multiplied by the amount of time between initial and final. And here I've written out the other one, right, the area under the curve that tells you how the displacement changes. So your displacement in the x direction is equal to your initial x velocity times the amount of time that's gone by. That's the non-accelerating part of the equation. And then if you are accelerating, you got to add a 1/2 at squared where the a is just the x component, right? And then you got to write it out a second time for your y components. And if it's a 3D problem, you'd have a third one in terms of z's, right? And the only thing that connects these two is time, right? The time will be the same because it's a scalar, but otherwise you just treat the components as completely independent variables. Now, in the end, if you need to come back and give me a magnitude like the total displacement and the angle of your displacement, or the magnitude, your final speed and the direction of your speed, then of course you have to reassemble those components using Pythagorean theorem and inverse tangent and all those other skills that we learned with vectors. But as far as problem solving, right, you're going to problem solve the scalar equations that you already know how to do all the algebra for the components, right? And so the solvability criteria is still you need three variables. Three of the five variables you must have known values for, right? Frequently there's a zero in there, but you need at least three on one of the sides, right? So you need at least three either x components or two x components in time or three components that go on the y side so that you can get a number out of one side. And frequently, the harder problems are, they ask you for something, say, in the x direction, but you actually only are given enough information to solve for it in the y. So what you do is you solve for time in the y, and then you bring it back over to x, since time is the one variable that goes back and forth. Trying to think if there's anything else about acceleration. Oh, yeah. So one final point, which is, although this looks like a system of quadratic equations that are linked, the algebra usually is never actually that bad because one or both of these acceleration components will always be zero, right? Always. And I'll show in a minute. I'll show you a trick whereby you can assure yourself that you'll never have to do a problem where you have non-zero a sub x and non-zero a sub y, which is a big deal to get a zero in there because as soon as you get a zero, you don't have a quadratic equation anymore, and it becomes a lot easier to deal with. Okay. So that's the application of vectors to kinematics. The classic 2D kinematics problem is projectile motion, which is just free fall, right? And so you get a zero here for a sub x, and your a sub y is 9.8 meters per second squared directed downwards. That's probably the only two-dimensional kinematic problem that you'll sort of like work to death. Let me move over to forces. Let's move this over here so you can see this. All right, so Newton's second law, right, that we've been solving, F equals ma. We have been doing this kind of covertly because I said to you early on, deal with the horizontal pieces and the vertical pieces separately, right? So now we can be a little bit more formal about that, right? I can't remember if we've been using the sigma notation or not, but it's super handy, right? That's the summation symbol for math. So that means you take all the individual forces and you add them together. once again, very rare that you're going to use the vector format. Like I was talking about earlier, maybe you would sketch it out to get a visual or something like that. But when it comes down to problem solving with numbers and you want a numerical value, you're going to pull that same trick. You're going to pull all the x components out, right? And so your net force in the x direction is equal to, it gives you your x component of acceleration, is mitigated by your mass. And then the same thing in the vertical direction. Now, there are as many terms on the left-hand side as you have forces in your free body diagram, right? And I encourage you to be formal about this at least a couple times. Oh, I don't know what that bell's for. In that you should write down, like if you have 4 forces in your free body diagram, then you have 4 terms over here on the left-hand side, and you have 4 terms over here. Now, half of them will be 0, or even more than half, right? So like if you have completely vertical forces, they wind up with zeros on the x component, right? Or if you have completely horizontal forces, then they wind up with zeros for the y. But it's a nice sort of discipline of mind to think about how many terms there are here as corresponding to the number of forces in your free body diagram, and then put the zeros, and then drop the zeros later, right? And you get a nice solvable algebra problem. Once again, the name of the game sometimes is like, for instance, when you have friction forces and you're going to use a mu, the model where you have mu times the normal force tends to be in this equation, the friction tends to be in that equation, and so that's a way that the two are connected. Mass is the one scalar quantity, right, that connects the two here. And like in kinematics, you can guarantee yourself one of these accelerations will be 0. And of course, frequently, if you see the words static, not moving, or constant velocity, then both the accelerations are 0, right? So now I want to explore a little bit this idea that you can always make one of your acceleration components 0, both kinematically and in terms of the forces. And to do that, the classic problem is the inclined plane problem. So I've got a little bit of a setup over here. Let's see if I can get the video on there. Yeah. All right. So here's what we mean by the inclined plane. Right. This is just a general case where you've got something, a plane that's inclined to the horizontal. And here's the tricky part. This is the part that gets confusing for students, is that the plane is inclined. The angle that's given in the problem is the angle of the incline, right, which doesn't correspond to the angle of either of the vectors cleanly. So let's walk you through this, right? So if you were to do your typical x is horizontal and y is vertical, which is something you need to move away from, right? First of all, x doesn't have to be horizontal. Y could be horizontal. But what I'm showing you here is that the Cartesian coordinate system, although you need x and y perpendicular to each other, you don't have to orient them along the horizontal vertical directions, right? In fact, the way you ensure yourself that one of your acceleration components is always 0 is either your x or y should always be oriented so that one of them is in the direction that you're accelerating, right, or in the direction of the net force. So in this case, we're going to take our usual x, y, and we're going to rotate it. I mean, you can do this a lot of different ways, but I'm going to rotate it so x is down and along the incline, so that's my positive x direction, which seals in my y direction as being up and to the right. And so here's what F equals ma looks like in this situation. The normal force now has become easier, right? If I hadn't rotated, this normal would be in quadrant 1, and it would have an x and y component, and gravity would have its usual, all the mg would be in the negative y. So it may seem like I'm just orienting it for no good reason if you just look at the forces, because what I gain for one force, I lose in the other one. But the key is the 0 for the a sub y, right? If I keep x and y like this, I'm going to have an a sub x and an a sub y, neither of which will be 0, right? Because we know it's going to accelerate down here in quadrant 4, so I'm going to have a positive a sub x and a negative a sub y if I don't tilt the axes. So tilt the axes, that's what I'm telling you to do. So here's what it turns out to be if you tilt them. So in the x direction, the normal force has a 0 component in the x, right, because it's all in the y direction. And then this is the tricky part, right? I'm not given the angle that the normal force makes with the x-axis. That is the angle that you want to use when you say, oh, I need the x component of a vector. It's the magnitude of the vector times the cosine of the angle, right? But in this case, it's not the cosine of this angle. It's the cosine of this angle up here, right? And that's 90 minus theta, right? So it's cosine of 90 minus theta, not the cosine of theta, because the theta given in the problem is not the theta mg makes with respect to the incline. It's the complement. It's the angle that the incline makes with respect to the horizontal, right? You got a little right triangle in here, so it's pretty easy to see that's 90 minus theta. And then this is the acceleration that's non-zero. That's the interesting acceleration, right? All the action is happening along the incline. Now, cosine of 90 minus theta is the same thing as sine of theta. That's usually what people will write down, right? One quick way to memorize the inclined plane is that the roles of the trig functions, the sine and cosines, are flipped. Sine theta, when theta is defined this way, is associated with the x direction along the incline, and cosine theta is with the y. I'll walk you through that in 1 second. There's no reason that you couldn't do the whole problem with cosine 90 minus theta, right? This is a trig identity. You should also see it in terms of the right triangle. The theta is opposite from the mg, right? So sine theta, right, is opposite over hypotenuse. The reason why sine theta is preferred, though, is because if you are solving for the angle, it's much easier to just take inverse sine, and then when you get that out of your calculator, that is the theta, right? Whereas if you do the inverse cosine, it's 90 minus theta, which is just like one more step. Plus, out of laziness, it's fewer pen strokes, okay? The y direction looks like this. The normal force is all in the y direction, right? So the entire magnitude of the normal force is that way. And then in opposition to that, you have a component, not the complete mg, but just a component that lies this way, right? And that's going to be the complement to the component in the x direction. So it's going to be mg sine, not of theta, but of 90 minus theta, so same trick, and minus mg cosine theta. And here's the zero that we were promised, right? The a sub y gives you a zero because we're not accelerating in that direction, right? So this trick of reorienting your x and y axes is how I can make that sweeping generalization that you are always guaranteed a zero either for your a sub x or your a sub y, or for both, right, if you have a constant velocity problem. So that is a trick worth bearing, right? And the rule of thumb about directing your axes, reorienting your axes, is if you know the direction of the acceleration, then orient either your x or your y, whichever you prefer, in the direction of that acceleration, right? Which is why oftentimes you'll see in a free fall problem when people just drop rocks or something like that, people will actually just define positive y or even positive x to be downward so that all your variables are positive, and it just makes your life a little bit easier mathematically. So there's a couple things here I want to point out. One is, how we're algebraically going to apply the components of vectors to the equations that we already know and love. And then the other thing is this liberating aspect of what x and y mean now, right? It's like everything in science. It's actually relative, right? So it's not like x means horizontal, y means vertical anymore. Read your mind. Okay? All right. Enjoy your problem solving.